Welcome to a video on the velocity, speed, and acceleration using vector valued functions. If r of t is a position vector value function and r of t is differentiable, then the first derivative of r of t will give us the velocity vector valued function. The magnitude of the velocity vector valued function will give us the speed, and the second derivative of r of t, or the derivative of v of t, will give us the acceleration vector valued function. And if we have a plane curve, it'll only involve the x and y components. And if we have a space curve, it'll involve the x, y, and z components. And you should be familiar with this idea from Calc 1. Let's go and take a look at some examples, and we'll also look at the examples geometrically. So if we want to determine the velocity vector, speed, and acceleration vector of an object when t is equal to 1, we first need to determine the velocity vector value function and the acceleration vector value function. So the velocity vector value function will be equal to the derivative of the given position vector valued function. So we'll take the derivative of each component. So the derivative of t would be 1, and the derivative of 0.5 t squared plus 4, we'd multiply by 2. That would give us negative 1t, or negative t, for the y component. To determine the speed, we would need to find the magnitude. So we'd have the square root of 1 squared plus negative t squared. That'll give us the square root of 1 plus t squared. And let's go ahead and find the acceleration vector value function. Remember, the acceleration is going to be equal to either the second derivative of the position function or the derivative of the velocity function. Well, here's the first derivative, or the velocity vector value function. So let's go and take the derivative of each of these components. The derivative of 1 would be 0, and the derivative of negative t would be negative 1. So this is what we needed to find in order to determine the velocity vector, speed, and acceleration when t is equal to 1. So to find the velocity vector, we'll replace t with 1 in the velocity vector valued function. So we'll have 1, and then the y component would be negative 1. The speed would be equal to the square root of 1 plus t squared, or 1 plus 1 squared. That'll be the square root of 2, which is approximately 1.4. And then our acceleration vector, or a of 1, is going to be equal to the component vector 0, negative 1. Notice the acceleration does not change when the value of t changes. Let's go and take a look at this graphically. So what we see here in blue is the curve traced by the position vector valued function. And then in red we have the velocity vector at the given value of t. And then this purple vector here is the acceleration vector. Notice that it does not change as the value of t changes. And the green vector is the vector that traces out the curve. One thing we should notice right away is that the acceleration vector and the velocity vector are normally not orthogonal or perpendicular. So if we pause when t is equal to 1, roughly right here, the velocity vector that we found is this red vector here. Its magnitude, or its length, is approximately 1.4, which represents the speed. And the acceleration vector that we found is this purple vector here. Let's go and take a look at one more example. Here we want to do the same thing. We want to find the velocity vector, speed, and acceleration vector of an object when t is equal to 2, given by this vector valued function. Let's start by determining the velocity vector value function, which will be the derivative of the given position function. Well, the derivative of cosine pi t, here we will have to apply the chain rule. Derivative of cosine u is going to be negative sine u times u prime. That's going to give us negative sine pi t times pi, or negative pi sine pi t. For the y component, the derivative of sine pi t is going to be cosine pi t times pi, or pi cosine pi t. And then the derivative of t squared divided by 2 is just going to be t. Now to find the speed, we have to find the magnitude of this vector valued function. It's going to give us the square root of negative pi sine pi t squared plus pi cosine pi t squared plus t squared. Now notice that both of these are going to have pi squared, so if we factor out pi squared from these first two terms, we're going to end up having sine squared pi t plus cosine squared pi t, and that's going to give us 1. So this is going to simplify nicely to the square root of pi squared plus t squared. Now to find the acceleration vector valued function, we need to find the derivative of the velocity vector valued function. Well, negative pi is a constant, and the derivative of sine pi t is going to be cosine pi t times pi. So we're going to have negative pi squared times cosine pi t. And then the derivative of pi cosine pi t is going to be pi times negative sine pi t times pi. So we have another negative pi squared sine pi t. And the derivative of t would be 1. Okay, well, this is all the information we need now to find the velocity and acceleration vector as well as the speed when t is equal to 2. When t is equal to 2, we're going to have negative pi times sine 2 pi. Sine 2 pi is 0. For the y component, cosine of 2 pi is going to be 1, so we'll have 1 times pi, or pi. And then for t, we'll have 2. And to determine the speed, when t is equal to 2, we already found the equation for the magnitude of the velocity vector. So when t is 2, the speed is going to be pi squared plus 2 squared, which would be 4. This is approximately 3.7. And then lastly, to find the acceleration vector when t is 2, we'll evaluate this vector valued function. So when t is 2, we'll have cosine 2 pi here. That's going to be 1. So the x component will be negative pi squared. Here we're going to have a sine 2 pi, that's 0. And then here we're going to have just 1. So here's our velocity vector when t is 2. Here's our acceleration vector when t is 2. And here's the speed when t is equal to 2. Let's go and take a look at this graphically as well. Okay, so what we're seeing here in light blue is the space curve defined by the position vector valued function. In gray we have the vector that traces out the curve. In yellow we have the velocity vector, and in red we have the acceleration vector. And right now it is set where t is equal to 2, so this yellow vector is our specific velocity vector that we found, and this red vector here is the specific acceleration vector that we found. If we rotate this, we get a nice idea of its orientation in space. Let's go ahead and trace out part of this curve so we can see the relationship between the velocity and acceleration vectors. Okay, that's going to do it for this video. I hope you found these examples helpful.